So this lecture is all about this subject here. And Sue and me were both involved with this, but the real heroes are Trond Torsvik, who is my buddy and colleague from Norway, which means that he has very deep pockets. He has access to a lot of money. And I've enjoyed that. We have enjoyed that over the years. And then there's Kevin Burke, who was one of my mentors. And he sadly passed away 2018, age 88. But four out of the five people here have some connection to WITS. And so I'll be describing this paper from 2010, published in Nature. You can see the title here. But the subject is all about, I'm going to tell you all about LLSVPs and deep mantle hotspots and large igneous provinces. We call them LIPS, kimberlites, diamonds, 4D mantle dynamics, earth stability, geodynamo, origin of life. It's pretty good for one lecture. So, I was thinking the other day that you can ask a geoscientist, what do you do, and it might be relevant to you to answer that question one day. And you could say things like, I explore for mineral deposits, or I try to find where the ore horizons are in a mine, or I figure out the isotope composition of the mantle, or I figure out the structure of this region. All of those things can be summarized together by saying all of us are, what we do is we try to figure out how the earth works. And that when people ask me that question, what do you do? I say, I study how the earth works. So that's what we're going to talk about in this lecture. Let's go to the next slide, Stephanie. So this picture is really the main one. So if you can understand what's going on here, you got this nailed. And so it's a cross section of the earth, and you see the core, which has got the outer core that's liquid and convecting, made out of iron and nickel. Then there's a solid inner core, also iron and nickel. You're late, but I won't make you sing. And then overlying the core is the bulk of the earth, the mantle, which is convecting also. And then it's proper to think about the crust, the Earth's crust, on a picture like this as just a very thin. I think of, when I think of cross section of the Earth, I think of the crust as paint. It's so thin it's just a layer of paint on a huge sphere. And then what's important for us in this lecture is LLSVPs. And they stand for the following thing: large, low, shear wave, velocity provinces. There's two of them in the Earth. And these are them, the orange blobs here, right on the core mantle boundary. So they're regions of the lowermost mantle, right at the core mantle boundary, that we think are very important in controlling all kinds of different things about the Earth. And so this name, LLSVP, large low shear wave, a very cumbersome name. Nobody likes to say it, but nobody has come up with a better name. Kevin Burke, my friend and mentor, he thought that, why don't I name the two of them after some of my heroes in my life? And so he named this one Tuzo and this one Jason. So this LLSVP on the right side, he called it Jason, but these names haven't really caught on, so don't worry about those names. So we can call this the Pacific LLSVP because it underlies the Pacific Ocean. And this one is important for us. The African LLSVP underlies the continent of Africa. And so important things to notice about them is that they really are antipodal. They are on either side of the core. And if you draw a line between them, the center of mass between them, that line would be pretty much perpendicular to the spin axis of the Earth. And so we might consider that these things might have something to do with the stability of the Earth. So, so what are these provinces? Well, here it tells you that they are hot. They're hotter than the surrounding mantle, and they're also denser than the surrounding mantle. Just kind of weird, but that's what the data seems to show. So we know that they're hot because in seismology, when you have low shear wave velocity, it either means that the material is hotter or a different composition from what's surrounding it. And in this case, it's both. So they're both hotter and denser than the surrounding mantle. And that is quite important. And we're going to try to show you that they have been stable for a long time scale in Earth history. So pretty much these things, we think, have been there forever and have been contributing to what we see on the surface of the Earth in various ways. Anything else should I show on this picture? So the picture also shows that, yeah, you all know about subduction. We have slabs sinking into the mantle, and some of them we can show quite clearly go all the way down to the core mantle boundary. And so, so what we're going to also show is that the edges of these LLSVPs are actually plume generation zones. And so you've got subducting material coming down, smacking into the LLSVPs, inducing mantle plumes coming off of these edges of the LLSVPs. That's basically the story. Let's go and show you next how we know about all of this. Okay, so here is the data from which we know about the LLSVPs. So here's a seismic tomographic image of the Earth at 2850 kilometers. So that's basically at the core mantle boundary. And what you see in red and orange are the low velocity regions. And there's two of them, Jason and Tuzo. So there's one under Africa, one under the Pacific. And if you make a cross-section of seismic tomography shallower than that, at about 2,000 kilometers, you see they almost disappeared. So they really are anchored to the core mantle boundary, and that's what their shape is. Go to the next picture. So what I'm showing here is that the seismic tomographic images are, you pretty much get the same result. So here are eight different groups of seismologists who are busy studying the Earth and analyzing and processing data from earthquakes, trying to figure out what the structure of the Earth is. And in all 8 cases, they come up with these objects that are called LLSVPs. So it's not just one group of seismologists that is proposing that we see these things. These things are real, and they are presently at the core mantle boundary, and they have this shape and position. And that's next one. Okay, so a lot of pictures that my friends Trond and Kevin show that relate to this subject are maps of the globe of the Earth, in which they have projected the LLSVPs, both of them, vertically from the core mantle boundary all the way to the surface. So at present, so you can see the continent of Africa is here, and underlying Africa at 2,800 or 2,900 kilometers at the core mantle boundary, you have this object called the African LLSVP, or Tuzo, and likewise for Jason. So this line, the red line, is I think it's the, let's see, what is it? Oh, okay. So here is the scale of a shear wave velocity. And there's the 0 point. So this red line is about the 1% contour of the LLSVP at the core mantle boundary, projected to the surface. And this line is going to become very important to what we're going to show you next. So let's see, what is it? 2 LLSVPs, Africa and Pacific, about a 3% shear wave velocity decrease. Yeah, 2 or 3, centered at or near equatorial antipodes. So they're really 180 degrees apart, perpendicular to the spin axis of the Earth. The center of mass are shown here in lat and long, and those are the antipodal positions. Okay, this laser pointer has died. Oh no, it's back. Go ahead, next slide. Okay, so what I'm going to show you now, talk about hotspots. And hotspots, as I guess defined here, and the red dots show you where they are. Volcanism unrelated to plate boundaries or rifts, widely attributed to mantle plumes from the deep mantle, but not all of them can be shown to be from very deep. Many of them may be caused by shallow processes. So you know what I'm talking about with hotspots. You all know about Hawaii, Iceland. There's one very close to us here at Reunion. These are all active hotspots, active volcanoes, big volcanoes, erupting lavas all the time. And I think the Hawaiian one is erupting at the moment. Big volcanoes or big lava flows happening. So we want to look at these hotspots and their distribution on the surface of the Earth with respect to the LLSVPs. So let's go to the next picture. Okay, so this one shows the positions of hotspots, present-day hotspots, filtering out only the ones that we can have a fairly good confidence that they come from very deep. And in these cases, we know that they're from deep because we can see them on tomography images. And this kind of thing is very difficult to do because the conduits that these plumes come up from the very deep mantle are very narrow. And it's damn hard to see them on tomography images. But these seismologists who do this kind of work are very talented and very mathematical, and they can see these things in these cases going all the way down to the core mantle boundary. So, for example, Hawaii, there's the Hawaiian one, and I'll show you some of the other ones in the next slide. But what you see here is something remarkable. So the hotspot positions all lie within a very close distance to the edge of the LLSVP in both cases. So, so they're right at the projection of the edge of the LLSVP if you project the position of that object to the surface of the Earth. So the next slide, I think, is focusing on the African one, just to show you some of the hotspots that we can see. Go to the next. Okay, so here is Africa, and here is the projection of the LLSVP to the surface. And the big pluses in red are all different hotspots that are deep ones. So for example, the Azores, the Canary Islands, the Cape Verde Islands, Ascension, Tristan, Kerguelen, Reunion, Afar. These are all deep hotspots whose positions lie very close to the edge. So it looks like all of these damn hotspots plot vertically right above the edges of the LL, but never in the middle. Why the hell is that? So the edges of these LLSVPs become important to consider as plume generation zones. Next picture. Okay, so let's take a slightly different tack and dig a little bit deeper into what this may mean. So we can show that at present in the Earth, that the plume generation zones at the edges of LLSVPs may be very important in the positions and the generation of these big hotspot volcanoes that we see all over the place. But can we take this into the past? Can we go into the geologic past and see if a similar thing might be true if we look at hotspots that are older than ones that are at present? So to do that, what you want to do is look at large igneous provinces or lips. So what these lips are mainly mafic. So we're talking about basalt, huge amounts of basalt lavas with a large areal extent and volume. So we're talking about basalts and related lavas, mafic rocks, with areal extents of maybe 1 million square kilometers and 1 million average of about 1 million cubic kilometers. So these are big magmatic events, and they're all in place in an intraplate setting. They have nothing to do with subduction, nothing to do with rifting or collision. They're caused from hotspots, old ones in the Earth. And another important feature is that short duration. So these are huge amounts of lavas that were erupted almost overnight, less than 5 million years, most of them within 1 or 2 million years. And a huge amount of igneous volume was in place over a huge area and volume in a very short time. So some good examples are the Deccan in India, there it is, the Paraná Etendeca in Brazil and its counterpart in Namibia. And the one that we are most familiar with here is the Karoo. This is a big one, the Karoo at 183. So one thing I don't like about this picture that my friends drew is it doesn't really show you the extent of the lavas. It does for example, for this one, CP, it stands for the Camp plume. It's 200 million years old, and you can find pieces of it in Eastern North America, northern part of South America, and in Northwest Africa. And so what you have to do to understand these in terms of LLSVPs, which we're going to do in a second, is what you have to do is reconstruct the continents to the positions that they were at the times when each of these different lips was in place. So for example, you know, you can see the separation between Africa, South America, North America. What you want to do is reconstruct that back together like a jigsaw puzzle. And then you can see that this Camp plume product all comes together as one huge, large igneous province. I think this is about the biggest one. It's 200 million years, and it's probably 10 million square kilometers. It doesn't really show the Karoo well enough because the Karoo is also huge. There's representatives in Southern Africa, in Australia, in South America, and Antarctica. So what we have to do is become very good at reconstructing the continents using normally common sense, jigsaw puzzle fitting, and paleomagnetism, in which we can quantitatively rotate continents back together to see where they were at the times when each of these different lips were formed. And they're all different ages. So the Deccan is a young one, 65 billion years. Paraná Etendeca, 132. Karoo, 183. But let me see the next picture. What this picture, the previous one, doesn't show is that it's something unique about Southern Africa in that we have four spatially overlapping large igneous provinces that have formed over about 2.5 billion years of Earth history. So there's 4 of them. There's nowhere else in the world where you see 4 large igneous provinces in the same place. So here they are. The red lines here are not LLSVPs. These are the boundaries of the cratons, Zim craton, Kapval craton. And the map shows the positions of each of these 4 large igneous provinces and where they occur with respect to the cratons. So the 4 large igneous provinces, from oldest to youngest, Ventersdorp, 2.7, and you can see the outline of it here. It's the pink one. And then the next one to come in is the Bushveld complex at 2 billion years. Yes, the Bushveld complex is a large igneous province, very likely caused by a deep mantle plume. Then the next youngest one is Umkondo, 1.11. That's the one in yellow. And these are huge magmatic events, which we can go and study the lavas at various places on the surface of the Earth. And then finally, the youngest one is the Big Daddy, the Karoo, at 182 million. That is the blue one. It goes all over the place in Southern Africa. Southern Africa was blanketed by the Karoo at 182 million years. Huge amounts of basalt erupted in a few million years, let's say less than 2 million years. And this is a picture that I drew, and it shows the plume impingement spots. And I like to think, kind of fun to think that, these plume impingement spots have been dancing around Johannesburg for the past 2.5 billion years. And it's really going to be fun to be here when the next one comes in. So there is going to be a next one, and it might be right under Joker. That's going to be a lot of fun. Okay, go to the next picture. All right, so I told you that what we have to do with respect to the LLSVPs is rotate the continents back to the positions at which they were at the time when the large igneous provinces were emplaced into the surface of the Earth. And so here on this map, in red dots, it shows you all of the different LIPs, lips, with respect to the margins of the L. And again, look at that. All of them are very close to the edge, not the middle and not anywhere else, but they're close to the edge of the LLSVPs at all kinds of different ages. So what this means is something really important. It means that the LLSVPs have been in the same place in the Earth for at least the last 200 million years, and maybe much older. So the LLSVPs, it says, from the distribution of blips, the stability of the LLS can be seen back to at least 300. Where's the 300? What? I don't see 300. Oh, the SCLIP. There it is. The SCLIP stands for the Skagerrak Centered Large Igneous. This is the one over Norway at 300 million. So almost all of, there's one exception. The Columbia River, large igneous province, very young one, 15 million, doesn't seem to be plotting where we want it to. What is the reason for this? We just don't know. It could be that the Columbia River is not one of these plumes that are very deep ones. It could be it's a shallow one, or there could be some other reason. But this one is a bit of a fly in the ointment. We have to admit that. But look, it's almost 80, 90% of them that are plotting very close to the margins. Next. Okay, so this puts it all together so far. The the hot spots. So these are the yellow circles with the black stars in there, the present day hotspots, Reunion and Afar and so on and so forth, and the large igneous provinces in yellow, green, big green dots, all showing a remarkable pattern of something near both of these, the edges of the LLSVPs, Pacific and African. So deep sourced hotspots and reconstructed lips, adjusted to the paleomagnetic frame that allows us to reconstruct the continents. And they're all within the margins of the LLSVPs. So plumes that gave rise to emerge from the edges of the LLSVPs. And those are places at the core mantle boundary that are going to have a high gradient in shear wave velocity. And the other important thing is that these LSVPs seem to have remained at the same positions, antipodal in the Earth, at least for the last 300 million years. So are the LLSVPs only a current phenomenon? No, it looks like we can track them back at least to 300 million years and probably much older. Let's go to the next picture. So here some of my friends have considered a reviewer's comment. They're going to say, well, this is just a matter of chance. So how likely is it that this distribution occurs by chance? And the answer is 1 in 7 million. So the probability is very strong that this correlation is real and that it's telling us something important about how the Earth works. Next one. Okay, now, I don't remember who it was, maybe Sue remembers, but one of us suggested that, why don't we look to see, was it you who suggested it? Sue Webb is the hero here. She said, why don't we look at kimberlites to see what the hell they may show in terms of the processes that we're interested in. And here this background picture shows Kimberley and the, what do we call this? The big hole in Kimberley. And so here is where we begin to get something very interesting with respect to economic geology, because diamonds. So here's a nice chunk of kimberlite with a beautiful diamond stuck into it. And so what we're going to demonstrate is that kimberlites also show this pattern with respect to the LLSVPs. And so kimberlites erupted in the past 540 million years, also going to show this pattern. So go to the next picture. So there's several thousand kimberlites that have been identified. And on this map here, the white dots are only the ones that have been dated. So the data set, which Sue stole from De Beers, I think, well, borrowed from De Beers, got permission from De Beers to use. So we're filtering out all of the ones that have not been dated. So the white dots are all of those that we have ages for. We know when they form. And so here they are on a different map that shows something very important that you all know already, that the cratons in the continent, which we can define as very old pieces of the continental lithosphere that have been stable for a long time, 2.5 billion years or maybe more. And those are shown in color of purple and green. The kimberlites seem to show a relationship. Well, they don't seem to, they do show a relationship to the position of these cratons. And so it becomes very important to study the positions of these kimberlites, to use them as a diamond exploration tool. Furthermore, you may know about something around here we call Clifford's rule. Tom Clifford was a professor here for many years, and he noticed that, I should have a picture to illustrate this, but I don't. He showed that if you take a subset of these kimberlites and look at only the ones that carry diamonds, as opposed to the ones that are barren of diamonds. Those with diamonds only occur above or within the oldest parts of the craton. And the ones outside of the craton don't have any diamonds. So this was used, and it's still being used by companies like De Beers as an exploration tool. You go find a craton somewhere in the world, you forget about the younger parts of the Precambrian, you look to the oldest parts, and then you go hunting for kimberlites. And if you find them, they are going to be likely to carry diamonds. So that's an important exploration tool. Here we're going to suggest that we have another important exploration tool for diamonds. Next picture. Oh yeah, so here's a picture of Trond, and I don't know what the hell he's doing. It's a very dark picture. What's he doing in his right hand? Is that a pen maybe? But in his left hand, he's holding a piece of kimberlite. So there is a piece of kimberlite that's 90 million years, so a Cretaceous kimberlite with a diamond in it. I don't know where he got this piece. It's maybe in a very fancy museum somewhere. But here's a nice kimberlite with a diamond in it. The diamond is 3.2 billion, very old. The kimberlite itself is very young, 90 million. So it's an important point. The diamonds, all of the diamonds that we see in kimberlites, they're all very, very old compared to the age of the kimberlite. So the idea is that diamonds are sitting around waiting in the continental lithosphere for kimberlites by chance to come through them, and take them as passengers, as lucky or unlucky passengers to the surface of the earth where we can collect them. So here's a relevant feature about kimberlites is they come up really fast. 60 kilometers per hour is an estimate of how fast they travel. So 3 hours from their site of origin in the mantle lithosphere, maybe 150, 200 kilometers deep to the surface in 3 hours, carrying diamonds with. So they're spectacular objects. Next. Okay, so here's a histogram of ages of a couple of different things. And I tried my best in the past few days to figure out what these blue histogram bars, and I don't know what the hell they are. So please ignore the blue ones. So what we're looking at, the yellow bars are kimberlites, and you see there's a big peak of kimberlite formation between 50 and about 150 million years ago, centering on about 100 million years ago. So Cretaceous is a very important time for kimberlite formation. And on top of that, Trond has plotted in red bars the ages of large igneous provinces. You can see some of them here. He didn't identify the Karoo, but Karoo is number 10 here. With various others. So there's also a concentration of large igneous provinces at about the same time. And this begins to give you a hint that large igneous provinces and kimberlites might be related to each other. And that's the way I think about kimberlites. I think of them as igneous rocks, igneous bodies that formed from heat coming from plumes that were derived from the deep mantle. And so kimberlites and lips are relatives of each other. They have the same age distribution in geological time. And we can think of petrologic reasons that I won't go into to connect kimberlites to large igneous provinces. But let's go on to the next picture. Okay, so what Trond has done here is he's taken this map that he likes of the whole Earth, and he's marked the position of the LLSVP, and then he's begun to plot the positions of where kimberlites occur. And these are kimberlites occurring about 160 million years ago, 155 to 165. And look at this. Again, you can see that they're only at around the edges. God damn it. I mean, that's important. Let's go to the next picture and see. Here he's got a series of time slices from 200 million years ago all the way up to 130 million years ago, plotting the positions of kimberlites at various times. And I'll show you a summary of all this. But you can begin to see that they're always at the edges of these damn LLSVPs, a truly remarkable pattern from the Gondwana continent. At all times, kimberlites eruptions took place near the 1% slow velocity contour. Statistical arguments that the coincidence of reconstructed lips with the margins is extremely unlikely to be chance, 1 in 7 million chance. So these things are real, and they are not random. They're not pure chance. The LLSVPs are controlling the positions of hotspots, kimberlites, large igneous provinces. Go to the next one. Yeah, okay, so here's everything put together. Reconstructed large igneous provinces, the green circles, the active hotspots, the yellow circles with the stars in there, and now the kimberlites. So all of these damn things are around the edges of the LLSVPs. So these are ones, so for the kimberlites, it's ones that are less than 320 million years ago. I think the next picture will show kimberlites that are older. Yeah, so these show the older kimberlites. There's not very many of them, but there are some. And so we can reconstruct the continents as best as we can back to 540 or so million years ago. And again, you find that these kimberlites, these black dots, are the ones in Siberia. And then there are other ones in Southern Africa. So the ones that I know about around here would be the Venetia kimberlite. It's 540 or so. There's another one at 540. I can't remember the name. So once again, even the older kimberlites are around the edges of the LLSVPs. Next picture. Okay, so here is something really important if you work with De Beers and if you're an exploration geologist looking for diamonds. There are no kimberlites, or virtually no kimberlites, in the core of Gondwana during the period 500 to 370. There's a few, but not very many. So why is that? And here is the answer. Look, so here is Gondwana at 500 million years ago. And you can see that most of Gondwana, almost all of Africa, was not underlying an LLSVP. It's a little bit of kimberlite activity down here in the southernmost part of Africa that you can connect to the African LLSVP. But elsewhere in the earth and all the rest of Gondwana, there is no kimberlites. Why is that? And the reason is because Gondwana was located between the LLSVPs and not over the LS. So therefore, you're not going to have kimberlites coming through if they are expected to be derived at the edges of the LL, which we think we can show. And so this could be a very valuable exploration tool. What you do is you look at the position of the continents at various times in the past, and then you look at where they are with respect to the margins of the LLSVPs, and then you go to those places and you look for kimberlites. And if you find some, they're likely to have diamonds, assuming that you've got craton material in the regions that you're looking at. So this LLSVP thing can be a very valuable exploration tool, not only for diamonds, but maybe also for stuffs that you associated with large igneous provinces, bushveld complexes, nickel, iron, chrome, platinum deposits, vanadium deposits, this kind of thing. So, if you're an exploration geologist, you want to pay attention to this thing. Go ahead. I think we're almost done. No, I'm not supposed to have this picture, but okay, so go to the next one, next one. Yeah, let's, this is the last one. So I promised to relate the LSVPs to a whole bunch of different things, and I'm going to try to do that now. So the implications of the stable LLSVPs. Remember, these are big objects at the bottom of the mantle, right on the top of the core, and they generate plumes at their edges. So here is where the kimberlites are going to come from, and all the large igneous provinces and the active hotspots. So we can explain from these LLSVPs the origin of deep mantle plumes. And the idea here, we still don't know why it is that it's only at the edges, but we can speculate that it might have something to do with subducted material going down in subduction zones all the way to the core mantle boundary. And then they are in convection motion at the top of the core, and they're dragged or swept to the edge of an LLSVP. And it is that interaction of the subducted material, this what they call the slab graveyard, with the edge of the LLSVP that is responsible for these plume generation zones. So we're still trying to understand the details of how that works. What might also be important about the LLSVPs, if you notice their positions, and here, Stephanie, have you talked to them about the geoid?
Not yet.
I still don't know if that's yet. Okay, but the geoid is the shape of the Earth. So here you can see that the Earth is pictured here as a perfectly circular spherical object, but that's not really what true Earth is shaped like. It's different from that, and it actually bulges at the equators. And so these dashed red lines are showing you the actual shape of the Earth. We call that the stable geoid, and you can see that the geoid has a definite correlation with the position of the LLSVPs. So it may actually explain why it is that the Earth has the shape that it does, because you have this hot, dense material that is pushing up maybe the entire mantle to stretch out the geoid in this shape. Of course, the other important thing is stability of the Earth's rotation. So remember that these two LLSVPs antipodal and perpendicular to the spin axis of the Earth. The Earth is spinning around, and it might be that these LLSVPs contribute to the stability of the Earth's rotation. So the position of these damn hot and dense things at the base of the mantle may explain why the Earth doesn't wobble all over the place when it's rotating. So these may be very happy things for us to have, because otherwise the Earth would be spinning in all kind of weird and funny directions. That also has important consequences for geodynamics. Let me talk about this in a second. But the origin of life. So the idea here is that the LLSVPs, being hot, dense objects, they're stuck to the core. The outer liquid convecting core is the part of the Earth that is responsible for the geodynamo, the Earth's magnetic field. And so as long as the Earth is convecting happily, then we're going to have a magnetic field. The outer liquid core stopped convecting, we are dead. There will be no magnetic field, and all of the creatures on Earth will die because of cosmic rays and ultraviolet rays from the sun, and it's going to be very bad news. So we've got to have a convecting core in order to sustain life. So what this story here is that it might be that these two LLSVPs actually are insulating the core, and they're preventing heat loss from the core and allowing convection to be happy and stable and contribute to the geodynamo and keeping life happy going as long as the Earth's core is convecting, helped by these two LLSVPs. So as LLSVP reduce heat flow out of the core. So without the LLSVP, the Earth's outer core should theoretically be frozen. So the whole core maybe would be crystallized and solid, and then the magnetic field goes away. So it protects us from cosmic rays, solar rays, and it will basically kill us all. So without it, no life on our planet, or at least it'd be very different, and there would be no class today. So the last thing is this dynamo story, and here an interesting observation that my friend Tron made. So here's this histogram of what is it? What is the yellow? The yellow is kimberlites, and the red is large igneous provinces. So you see there's this peak of activity, of magmatic activity at about 100 million years ago, between 50 and 150. And the question is, does that have anything to do with the Earth's magnetic field? Stephanie, have you taught them about reversals in the Earth's magnetic field?
They will be doing it next week, but they did learn it a bit at the beginning of the year.
Okay.
If they did apply.
Well, you're all familiar with the idea that the Earth's magnetic field sometimes will flip. The North Pole will suddenly become the South Pole, and it flips back and forth like this in some kind of cyclic fashion. You can see, so zero here. So we're looking at this curve here, and it shows you the changes in the magnetic field from positively oriented to negatively oriented, back and forth over the course of geological history. But then in the Cretaceous, there is a long period where there is no geomagnetic reversals. The magnetic field seems to have been stable in the same place and fashion for a very long time. And they call this the Cretaceous superchron. And Tron was asking the question, could this have anything to do with this period in Earth history when you have a lot of kimberlites, you have a lot of large igneous provinces, all constrained by the LLSVPs. And so the idea here is that the LLSVPs at that time produced a lot of igneous activity, a lot of plumes coming off the PGZ, and that contributes to a more stable convection system in the Earth's core, and much less chaotic reversals. Whether or not this is true, we don't know. But I asked Tron about this last night, and he answered, well, you know, this slide that I showed is a very old one. So it's maybe 10 years old, so 15. You know, this work that we're talking about is not new. This is 15 years old, but it's okay because look, Sharon gave a talk last week. He talked about work that was done 400 years ago. Anyway, so he said this is an old picture, and the people who study the geodynamo, so these guys who model core convection, stuff that is way beyond me. Sue will know much more about it. But he says, yeah, these guys in the beginning, they said that this Cretaceous superchron could have something to do with, at that time, the convection pattern was more stable, leading to a more stable magnetic field. But he said now they've changed their mind, and actually it's the opposite. So it should be more chaotic if there's more plumes coming off it. So what does that tell you? It tells you something very important about science that I'm going to share you with my opinion here, and that is that modeling is something that you have to be very cautious about, because modeling, which means that they just use computer code to study certain features or certain processes in the earth without looking at any observations or data. If you just look at the core convection, you can propose anything the hell you like. So they could change their mind. One day they think it's stable, the next day they think it's unstable. So be careful of modeling. And I always run when I see it's only modeling being done. Anyway, I think that's the end. Go to the last picture. Yeah, I think this is the last one. You can go now. No idea what time it is, but so this is a little animation